Hi everybody, in this video we're going to talk about linear regression and the way that we can derive the method for finding a best fit line. And I've borrowed some of this material from a webpage that was made by Ridley Leasy. The link is up here, and I'll try and share this notebook with you guys so you can have a look at it after the video's over. So we've been talking about calibration, and let's say we wanted to calibrate some wind speed sensor, and we subject that sensor to some known wind speeds in our wind tunnel, and they range from something like 0 up to 20. And then we look at the voltage that's output from this imaginary wind speed sensor. And we're doing this so that later on, when we put our sensor into the field and we read the voltage, we can correlate that voltage back to a wind speed. And so you can see that this data fits some sort of linear trend. Maybe something that looks like this. And we have all these data points that make up that trend, and we call these data points each of the x values, the wind speed values, xi, and each of the voltage values, yi. And so we could try some number of lines of best fit. We could adjust the y-intercept by moving it up or down to try and find the best fit. And we could also adjust the slope to see if we can find the best line that fits that data. Well, you can do that with your eye, and you can probably get something that's pretty good. But you can imagine a case where it's not really that easy, and the line that you draw might not be the same as the line someone else draws. And they both might look to your eye like a pretty good fit. So we're interested in a way of quantifying how good that fit is so that we can figure out which line, which slope, and which y-intercept is actually the best. And so we'll call the equation for that line, the best one, something like y-fit equals our slope, m-fit, times our xi values, or x-fit values, whatever values you want, plus the y-intercept. That gets us our fit. So how can we actually do this? Well, we kind of want an idea of how far each of these points is from our line on average. So you know that there will be something in here. We're going to add up all of those distances, like these. And maybe take their average. But if we did that, that would be a little bit problematic because some of these distances are above the line, and some of them are below, and some are going to come in as positive, and some are going to come in as negative. And so we know in general how we deal with that with a single quantity where we want to know how spread out the distribution is. We square those differences from the mean and develop the quantity that we call the variance. And so we could do that here too. We could develop some variance estimator for how far these points are from the line. And we call that our cost function. Or we call at least the numerator of that our cost function. So if we developed that variance estimator, it would look something like this. That variance estimator squared is s squared. And this should look pretty familiar to you by now. It's the sum from I equals 1 up to n, which is the number of calibration points that we took, where we take the difference between yi, our calibration values, and our y fit value, and then we square it. And then in this case, we have some n minus 2 in our denominator. So we have this variance estimator value. And this part is really interesting, right? This is the difference squared summed up. And we could call this something like a cost function. And that's the terminology that's often used. So we'll say that the cost associated with how far this point is that difference squared. And so if we want to minimize that cost, we would find the line that on average best reflects the shortest amount of distance between all of those points and the line. So we can do a little work on this and develop something that we call the sum squared of the residuals. Remember, the residual is the difference between the fit and our y value. But remember, our y fit value is just our slope times the calibration value plus the y-intercept. So we can sub this equation in here into our numerator, our sum here, and that helps us look at what our cost function actually looks like in terms of our slope and our y-intercept. So we call this the sum squared of the residuals, the SSR. And that's going to equal this numerator with our y fit plugged in. This is going to be the sum from I equals 1 to n of yi plus m fit times xi plus our b fit value squared. And so now we can say that if we minimize this function SSR, we have found the minimum cost associated with our fit line, and we have found the line that best fits our data. Now remember, this is an estimator of the actual slope that exists in this line, in the trend that really exists in our sensor. So remember, just in the same way that if you were to measure a quantity 10 times and take the average, that quantity, let's say the mass of some object, that object has a real mass. If you measure that object's mass 10 times and then take the average, you might not get the actual value of that mass, but you've got something close, some estimator, right? And so too with this. We are trying to find the estimated value of m and the estimated value of b. And so before we try to look at the minimization of this function, let's expand this polynomial here so that we have some more simple terms that we can work with. So this is going to equal, we still have our summation, but we're squaring this, right? So we have to use FOIL from algebra, first, inside, outside, last. So our first term is going to give us a yi squared. And then our inside and our outside is going to give us 2 of the following quantity, 2 times yi times mfit times xi plus bfit and then we're going to have our last term squared. And our last term itself is a binomial, so we'll have to do FOIL again on that. And so when we do that, we will get our bfit value squared plus 2 times bfit times mfit times xi plus mfit squared times xi squared. Okay, so I know that looks harder to deal with, but it's actually easier. Why? Because if we're looking for the minimum of our cost function, the minimum of this SSR function, just as a reminder, this is our cost function. If I'm looking to minimize this, how do I find the minimum value of any function? Well, remember from calculus, if this is a function f of x, and this is x, and the function looks like this, how do we find this value here, this critical point? Well, we take the derivative, and the location where the derivative, the local slope equals 0, is guaranteed to have a critical point. In this case, we are taking for granted that that critical point is going to be a local minimum and not a local maximum. In fact, we're going to assume that it's a global minimum, which is okay for today. So we are going to take the derivative of this function. So what happens when we do that? Well, which derivative? Well, we have two quantities that we need to minimize. So we're going to take the derivative, or at least the partial derivative, with respect to each of the quantities that we want to minimize our cost function with respect to. So we want to minimize the cost function simultaneously with respect to the slope and the y-intercept, because if we choose the wrong y-intercept, there's going to be a slope that minimizes the function for that y-intercept. So we don't want to choose one arbitrarily, we want to minimize both of them at the same time. So if we take the partial of SSR with respect to our slope mfit, what are we going to get? Well, we still have our summation. And we should get from this term a yi times xi times 2 here. One sec. So from this term we should have a negative 2 yi times xi. Let me get my pen working. Here you go. Negative 2 yi times xi. And then where else do we see mfit? None there, 1 here. So when we take this derivative, we're going to get a 2 times bfit times xi. So and here we are going to get a 2 times mfit times xi squared. So now we're looking for the location where this derivative equals 0. So we set this partial to 0, and then we can distribute these summation symbols into each term. So you can pull out the negative. And we can also divide each term by 2, because 0 over 2 is still 0. And so when we do that all together, we get minus the sum of I equals 1 to n of xi, yi, plus b fit, which is a constant, multiplied by our summation from I equals 1 to n xi, plus our slope m fit. That's the sum of I equals 1 to n xi squared. Now, let's set this aside for a minute, because we don't quite know what b fit is. And so we're going to take a look at what b fit might be so that we can solve for m fit. So now let's take the partial of SSR with respect to b fit. So now we're going back up here. We're going to take the partial of this with respect to the b fit value. And so we should get the sum from I equals 1 to n of, well, we'll have a b fit times negative 2 times yi up here. So we should get a negative 2yi. And we have a b fit squared. So we'll get a plus 2 b fit. And then we have a 2 times b fit times m fit times xi, so that when we take that derivative, we'll get 2 times m fit times xi. Now we can set this derivative equal to 0. And we can pull out the 2 from each of those and divide by 2. So 0 over 2 is still 0, so we're left with our summation from I equals 1 to n of negative yi plus b fit plus m fit times xi. And then we can distribute each of these. And because the sum of yi from I equals 1 to n is going to look like our number n times the average y value, we will get negative n times y bar. And actually, maybe I should explain that just a tad more. So what is y bar? Well, y bar is equal to the sum from I equals 1 to n of yi divided by n. Well, the term that we have is negative this, right? Sorry, this is y bar. So if I have this term and I multiply by n, I have a negative over here because I'm turning this negative. So now if I multiply by n, I get negative n times y bar is equal to the sum from I equals 1 to n of yi, which is exactly the term that I have here if I distribute this sum. So I can replace that term with this directly. And then for my bfit term, my bfit is just a constant. So when I sum from I equals 1 to n, I can pull that constant out, and we just get n when we do that sum, because we add up the number 1 n times. So we say plus n times bfit and then for our mfit, we were summing I equals 1 to n of xi. So we'll remember that's the same as just what we just did with this yi. We should get n times the average. So here we're going to get mfit times n times x bar. And so we can divide all of this by n. The n's will fall out. And we can solve for bfit. And so bfit is going to equal y bar minus mfit times x bar. So now we have a nice simple equation for bfit in terms of mfit. And so we'll go back up and we'll plug that into this equation where we had bfit here. So just for ease of explanation, we'll call this equation 1, and we'll call this equation 2, and we'll say so equation 2 into equation 1. And so when we do that, we would get 0 equals negative sum from I equals 1 to n of xi, yi, plus, here's where a bfit comes in, that's y bar, minus mfit times x bar. And then this is the sum, I equals 1 to n of xi, plus mfit times the sum. So now we can solve this for mfit. We factor mfit out, we move this over, and then we divide by what's left, and we get the following. Mfit equals the sum from I equals 1 to n of xi times yi minus y bar divided by this sum, which in the end you will recognize is what we just out gave you from last class. So given these two equations for mfit and for bfit, so bfit was equation 2 and mfit was equation 3, if we use those two equations, we find the estimators of m and b that best fit our data.